So in an hour and a half, you'll be done with lectures on resurgence. So we've, up to now, we've seen on a second order linear ODE how, one solution can turn into two solutions by analytic continuation, because instead of having a convergence series where your asymptotics is the same all throughout, meaning changing the argument of your variable in the complex plane, here it's not true. You actually have different type of asymptotics in different regions in the complex plane, and we saw this for the area function. Then we went into a nonlinear first order ODE, where we saw that instead of a single two solutions or a single type of exponential, we had an infinity of them. That was, it comes from the fact that our solution, our equation was nonlinear. And so from there, we started trying to construct, again, the discontinuities, which is basically the difference between a resummation, a Borel resummation, before and after a Stokes line. So basically, all the exponent, in this case, it's not just a single exponential that gets turned on, it's all of them that get turned on. What do they get turned on by? There was these Stokes constants that appeared directly, that you could see directly from these Borel residues. We made the relation between the Borel residues and the Stokes constants as well. So the Borel residues is whatever comes, the constant multiplied your singularities in the Borel plane. But these depend on the sector that you're analyzing and the singularity that you're looking at, while the Stokes constants only depend on basically the final sector, so the singularity. So I told you a little bit about bridge equations and the fact that you can use them. If you have a Tron series, you can use them to actually predict how the discontinuity is going to look like. And finally, we finished with a small analysis of the large order behavior. What was the biggest take I wanted you to see from the large order behavior was that you're analyzing the perturbative series, right? You calculate the large order behavior and you see the first exponential. But you don't only see the first exponential, you see the second one. One came multiplied by S1, the next one came multiplied by S squared, the third one would come multiplied by S cubed, where S is the Stokes constant. So again, all sectors in the trans series resurge in the other sectors, basically. In the large order of one sector, you can see all the other sectors. So today, what I would like to do for you a little bit is I want to finish this discussion with what's called ambiguity cancellations. And then we will finish the lectures with some results on summations, because at the moment, everything I explained so far is I can write a formal solution. All these sectors, perturbative, non-perturbative, are all related, but I haven't told you. But how do I, well, meaning we've talked a bit about Borel summation, right, and optimal truncation, which gives you a number, an exponentially accurate number, but we haven't really spoken about how to go beyond this local region that we're talking about, and how, more than that, actually, can we understand global analytic properties of our observable from just this formal completion of the observable, which is what the trans series gives you. I'll finish my coffee. Eventually, it'll do something. So, what is ambiguity cancellations? So, as in many problems in physics, the problem that I was talking about this last lecture yesterday, and it's something that we already mentioned. So I'm interested in what? I'm interested in Z real, right? It's a time. For me, that Z in that equation is time. I'm calculating things at late times. So I'm interested in doing an integration for Z real. But if you do remember, so this is in the Z plane, well, actually in the Borel plane, but for Z, so I want to do an integration that will give me a solution for Z real, which means that I would like to do a Laplace transform in the direction of Z real. But Z real is a Stokes line. It's where all my singularities are. So I had these cuts, meaning I'm putting them away from the real axis. Of course, if you plot them in Mathematica, they'll be all on top of each other, but it's the cuts. And so, as we've seen, the only way that we could do this was by, let me ignore that part, is basically doing a lateral resummation. So this is 2a, 3a, etc. So lateral resummation, here I have S plus, here I have S minus. But as naturally, what this will give me is basically an ambiguity. Is my result given by S plus or by S minus? Is it given by a combination of them? How do I combine both results in order to get a final result that makes sense? So what we want to find is a summed result for argument of Z equals to 0. But it's a Stokes line, which is a Stokes line. So then there's a question. Do I do S plus or S minus, or what do I do with difference? We know that this is what is called an ambiguity in the resummation. So we need to know how to actually properly sum this. And I know that my difference, if you remember so of the perturbative series, this was given by the discontinuity, and that is basically and remember that I needed to resum this because all the sectors will also have, sorry, this is K, will also have ambiguities in the same direction. So this is actually, so how do we make sense of a single summed result? But we should not worry about just the perturbative series. Why? Because I know that my whole solution should be given by the whole trans series, so not just by the perturbative series. So, in particular, what I know is that not only the S plus and S minus of the perturbative series have, but S plus minus S minus of all of them have. So I don't know if you remember, I mentioned this in passing, that the Stokes constant, which is S1, is actually an imaginary number. This means that at least to first approximation, this ambiguity from phi 0 and phi plus is imaginary. So It'll have a real part and an imaginary part. So the first question is it removing this imaginary part enough? Or do we need to do a little bit more work to understand how to define the object completely? So as I mentioned, what we have, so this is all true for any sector. So this is always different from 0. But what we want is to define basically a real solution of the Tran series. Sorry, this is Z sigma. So remember that the Tran series of Z sigma is sigma to the n, e to the minus n, a z phi n of Z. So it's a sum over all sectors. But what I want to define this is some sort of resummation of all these sectors, so some sort of resummation of the Tran series that resums this in such a way that I get my final result without ambiguities. But I have one more thing. I don't have just the resummation of the phi n's. I have a parameter sigma, which is in general complex. So, so just to say, sigma is in general a complex number. The coefficients of the phi n are all real. You can check this from the equation, but they're all real. So, and the question is, how can I have a balance between these lateral resummations and a definition of the parameter sigma such that I get an honest, real Tran series out of my result? And this is not, definitely not, taking just the real part of the Tran series, as we're going to see. So the answer is that there is a specific choice of sigma equals to some sigma 0 such that or not balances, but it cancels the S plus minus S minus imaginary part. So, sorry. Of the Tran series, of the full Tran series, is 0 to all orders for Z real. So how do we do this? Define S plus minus. Define, no, don't define, just write it as such. S plus. Acting on the sectors, on all of my sectors, if you resum, this actually corresponds to having, so this is basically going to be the real part of my resummation, and this is going to be imaginary part of my resummation for each sector. We have to remember that when we're summing each sector. So here it's phi L, phi L. So the imaginary part, remember the coefficients phi L do not have, are all real, which means that when I'm resumming this, It's because I'm resumming to e to the minus plus minus I epsilon infinity. It's because I'm summing just above the real axis or just below the real axis that I'm introducing the imaginary part. And then let me just try and see if I can construct this series. And you're going to have to believe me at some point that the construction actually works to all orders. This can be, again, I will write to you what it is in fact, but what I'm going to do is now start with the perturbative sector phi 0. So I imaginary of phi 0 is just that part, right? So it's 1/2 of s plus minus s minus phi 0. But I know that this is what I've written before. It's written there. It's the discontinuity. So this is equal to 1/2 of sum k greater or equal than 1, s1 to the k, e to the minus k, az, s0 minus of phi k. But now I want to write this S0 minus as a real part and an imaginary part. I can just write this is the -1 of phi k, and that's 1/2 of s plus s minus and 1/2 of s plus minus and s minus. So what I have here is 1/2 s1, sorry, s1, sorry, forgot the sum, s1 to the k, e to the minus k az, real part. I'm just going to write that this is the real part. I mean, this is the sum of the two s's. This is the subtraction of the two resummations. Real part of phi k minus I imaginary part of phi k. And this is because I have the s minus here. So now, what do I want? I want to cancel this. Well, do I want to cancel the imaginary part? Remember that the S1 is imaginary itself. So whether I'll want to cancel the real part or the imaginary part will definitely depend on which sector I'm looking at. But, sorry, I will end up, this is what happens after lunch, even after 2 coffees. So, what am I writing here? I'm saying that from the resummation, whatever resummation I choose, I want to keep the real part and I want to add something to the perturbative series such that I cancel this imaginary part. What am I allowed to add are the other sectors of the Tron series. So here I'm writing the imaginary part such that in order to cancel the next order, I want to see what I need to add to phi 0 such that this cancels exactly with this. But in order to do that, I need to rewrite the imaginary part and the real part of phi k. So in the same way as I've written for the phi 0, the imaginary part of phi k is just 1/2 sum L S1 to the L. So now there's an extra thing here because it's not the phi 0, it's the thing phi L. So this is the discontinuity of the sector phi L. And it gives me S0 minus phi L plus K. Phi K, sorry, not phi L, phi K. So this is the imaginary part of phi L. So just a second. Yes. If I look at here, what do I have first? I have S1 over 2, real part of phi 1, e to the minus az. I'm just writing the first few. Sorry. Am I missing something here? Ah, sorry. What I did, sorry, I have here, and then I will have an imaginary part of phi 1. If I now plug into, from there, the I imaginary part of phi 1 as being given by the first order of that expression, what I end up getting is minus 1/4 S1 cubed real part of phi 3 e to the minus 3az, and then I get plus, there's going to be e to the minus phi az, etc. So I can rewrite everything that I have here such that I keep only, meaning I keep only the parts that I know that I'm writing here, the real parts of phi, of the phi's. And then, of course, the imaginary part is coming because the S1 is pure imaginary. So if I write this, that means that what do I need to add to phi 0 in order to cancel this? I need to add all these terms, right? So, for example, if I imagine that I'm choosing to start by S minus of phi 0. If I'm choosing S minus of phi 0 and I add to it, just a second. So if I now choose, I'm choosing just one of the summations. And to phi 0, I add this term. What I'm in effect doing is canceling the first term there in the imaginary part. So what I get is real part of phi 0, because the S minus is a real part plus imaginary part. So real part of phi 0 minus I S1 over 2 imaginary part of phi 1 e to the minus az. So what I wrote here is like, I have a real part of phi 0 and I have an imaginary part of phi 0. That's what comes directly from the S minus. Real minus I imaginary. So that's these two terms. This term here comes from, meaning from expanding, but you have to say that here, because it's I imaginary of phi 1, what I have here, this is real. Because S1 is imaginary, I is imaginary, so this term is actually real. So I have this, and then I've added this term, because that's what comes from here. And I'm not just taking the real part, and there'll be an imaginary part which will be higher order, in any case, if I use this expression. What I want to say is that, in fact, if you look at what I've calculated for the imaginary part, this, the first term that comes from here, cancels exactly with the term that comes from here. So these two terms cancel, they're imaginary parts, and of course then there's higher orders. But the point being is that if you keep on adding there the extra contributions, so this is the first one that I would need to add to phi 0 in order to cancel. What's the next one? The next one will be, meaning in principle would be, you could say that I now only need phi 3. In fact, it's not quite true. That's why I'm saying that you need to believe me on this, that to be consistent, I would also need to add a phi 2 and a phi 3 and a phi 4 and a phi 5. I can't just add the ones that are here, because otherwise things actually will not cancel. But what I want to say is that if I kept on adding terms here, it would be an S1 squared over 4 phi 2, and there might be an actual S1 squared phi 2, e to the minus 2az, and then I'll have an S1 cubed, etc., etc., etc. In fact, if I kept on trying to cancel always the imaginary parts, what I end up getting here is S minus of the trans series Z when sigma is equal to S1 over 2. S1, S squared. Remember that the trans series, if you look there, is sigma to the n resummation, whatever resummation you're choosing. So in fact, if I just started with the trans series, with the perturbative series, in order to cancel all the imaginary parts that come from the ambiguity of choosing above or below the resummation, what I find is that I can't have just a perturbative series. I have to have the whole trans series with the parameter tuned to a very specific number. And what's that specific number? The Stokes constant divided by 2. This is actually something called medium summation. And I will, so this is what I called the real part, of course. And just to say that this is actually, so S medium is actually the same as choosing S minus of, we introduced the Stokes automorphism, by the way, of half the Stokes automorphism. That's why the S1 over 2 coming from and not just S1. The Stokes automorphism, so the Stokes automorphism gives you the jump across the Stokes line. Half the Stokes automorphism, instead of jumping by S1, you're jumping by S1 over 2. That's basically what it's doing. So this is the medium summation. One detail here is that, in fact, the reason why sigma is specifically S1 over 2 is because I chose to start with just the perturbative series. But in fact, if you chose, if you use medium summation, what you find is that what you need to fix is the imaginary part of the sigma. The real part is still allowed to be anything. So if I was to choose here some sigma r plus S1 over 2, this would be perfectly allowed. So you still have the freedom of some freedom of an initial condition, but not, but in order to have no ambiguity, you need to fix the imaginary part of the sigma. And that gives you, then basically, just to say that if I had the S plus instead of the S minus and did the exact same thing, instead of having the sigma equals S, the real part plus S1 over 2, I would get the real part minus S1 over 2. So it's basically kind of, you have the Stokes line, is kind of going halfway this way or halfway this way, and I'm just decreasing by S1 over 2 or increasing by S1 over 2. So a lot of problems do happen, meaning, of course, you can have Stokes lines everywhere, but if you have Stokes lines in the direction that you're trying to integrate, this is what you need to do. And in order to define it properly, unambiguously, you actually have that parameter needs, the imaginary part needs to be sigma 1 over 2. So now, what I would like to do is to go into just one thing. So yes, the summations of Tron series. So this, because the problem is that you can't go on the real axis. So if you choose above, you get some imaginary part. If you choose below, you get some imaginary part. It's not even just that, meaning I'm calculating for this problem, I'm calculating energy density. I want it to be real. So, of course, then you need to give the input of the physics. But my input of the physics, sorry, I didn't mention, but it's that I want my solution to be real. Yes, because I'm calculating a real quantity. Not one, all the imaginary parts cancel. Yes. So the idea is that you can, and it's completely unambiguous how to do this. Uh, well, in some sense, if you had logs, for example, you'd have to be a bit more careful about doing this. The procedure, you can always do it. It's not that you can't do it. But yeah, basically medium summation is pretty much what you need to do. But again, with logs, they can introduce 2 pi i's. You need to be slightly careful. But yeah, the procedure is exactly the same. It's it's pretty much, meaning again, imagine that you're calculating a series and your coefficients are not purely real. Then I can't guarantee to you that the Stokes coefficient is purely imaginary, but for these cases it is. In general, most of the cases it is purely imaginary. Exactly. You can play the exact same game. You can start again with the perturbative series and see how everything balances, and in all likelihood it's going to be the medium summation. But for example, in situations where you had imaginary phi's with imaginary parts and everything, and you wanted an imaginary solution, you're talking about like some different problem where you want a solution that is imaginary. Still, across the Stokes line, typically, meaning you will end up with some medium summation. There's other types of summations that you can assume in across any Stokes lines, of course. I would say so, meaning from the point of view of resurgence, it doesn't care what sigma is. So how you define, meaning if you wanted sigma to do 1/3, it's allowed, meaning you can choose, it's still unique solution, you can still find it. So if you don't have any physics input or initial conditions or something, then how are you defining the parameters? Because at the moment, I'm just saying it's an ODE, first order, has a parameter complex. Could be anything, yes. But usually, fortunately, we do have some physics behind it that kind of guides us to what we want.
So you still have sigma r, right? That's gonna specify in your code from before which one of the many solutions asymptotic to the perfect fluid that you're teaching.
Well, so sigma I is needed,
Yeah.
right? You
Is there an easy way to actually pinpoint the sigma needed to pick some initial conditions say at zero? No.
So, meaning the way we've done it is actually do so. In a lot of cases, you have, especially if you have a DOTE, obviously you can do this. You know the solution at zero. You know you can find even numerically the solution to all orders. So you can do a Taylor series. You can do the Taylor method, which is basically doing analytic continuation from zero to slightly away from zero. Asymptotics can get to there quite quickly. That's what we did, in fact. That's a good question. So unless you have some specific properties of the problem that allow you to compare solutions because again, you are doing the exact opposite direction, right? Zero and infinity, which means you're going as far away as you can.
Perhaps if there is a way we write the whole resurgence series as some integral, and then you can map this integral into something that is a nice expansion ability, then you can I see.
Sure.
But it's not generic, not even for one parameter.
Meaning, I think if you have other things like integrability and stuff, it can definitely help. But if you have a non-integrable thing, you can. So again, it's possible that what you can do, and this is a slightly different thing, is that as we're going to see, the problem has singularities in the complex plane by meaning as many functions do. So it has branch cut singularities. If you can compare, if you can take your solution to there and you know properties at this branch cut singularities, you can fix parameter there. So then what I would like to do now to finish up is talk about summations. And this means also reviewing a tiny bit about what we spoke before. So the first thing I would like to say is the optimal truncation and hyperasymptotics. So if we have our expansion, right? So I have the phi 0, which was equal to sum AK 0. So this is not K, it's N, doesn't matter. Z to the minus N. And then we know that the AN0 grew as N plus beta divided by A to the N plus beta. And I mentioned to you that for each value of Z, so fix Z, I'm assuming Z very large, we can truncate. So the optimal truncation means truncate at N optimal, which is given by, sorry, modulus of Z, AZ. So basically that means that I have my optimal value, the minimum error, which is given by this. So sum N equals 0 to N optimal minus 1, A N 0 Z to the minus N. And the remainder is of order E to the minus A modulus of Z. So this gives us exponential accuracy, but we know that we don't only have the perturbative series, we know that we have a series. So how can we improve on this error? Because we have, in general, all of the sectors. So in order to include more sectors, we need an extension of optimal truncation. Optimal truncation is not enough, obviously. So what we do is then hyperasymptotics. So this was constructed. Again, it can be proven by analyzing. How you do is you analyze the remainder. There's some integral equations for the remainder. You can actually check what the next order gives and what are the optimal points of truncating your series such that you get, again, a minimal error. So what I'm going to talk about is what's called level 1, hyperasymptotics, just briefly, which means to include phi 1. So then, in fact, what you need is, like, from the perturbative series, what you need to include is n, so this is means perturbative asymptotics, and then level 1 is 2 times so you're now including 2 terms. But you remember, if you remember, in my drawing, when I did the drawing of optimal truncation, actually, I can show you quickly, if it's still here somewhere. That's not what I wanted, sorry. Oh, that's, sorry, this is what I want to show you soon, not now. Asymptotics. That it went all the way to the optimal point, and then the error started increasing. So now adding 2 terms, obviously we're going, if we only include that, we would be like here, right? So we would be getting a much worse result. So and what you do is, like, so then in order to compensate that, you include the second sector, but you include the exponential sector in what is called hyperterminant. Again, these things can be proven via the analysis of the remainder, which I am not going to do. So this not only corrects the error of the extra terms that we include of phi naught, that we include of the perturbative series, but also, in fact, decreases. Can anyone tell me how much do you think it's going to decrease the error by? Another exponential, because that's the next exponential that you have to include, exactly. So actually, so the overall error, so the remainder would be of the order e to the minus 2a mod z. So to do this, 3, 2, but it's not enough to do optimal truncation of phi 1. That's the thing, the problem with doing this to higher and higher orders is actually that I'll write to you what we have to add. And it's actually, meaning there's a formula, and there's formulas, but the formulas become more and more complicated. So in the end, meaning this is good because it doesn't, how do you say, it really, you can do this, you don't have to integrate for each z, right? So in that sense, it's a faster way if you include a few, but the expressions become really complicated. So the number of terms that we need of phi 1, like in some say of optimal truncation, would be now n1, and this is still a level 1 because, again, we're only including phi 1, is now, so basically, modulus of AZ. The original value for optimal truncation of phi 0. So this is what you'd need for phi 1. But then, and I'm going to write the expression, but it's not pretty. So the F hyperasymptotics of level 1 of Z sigma is equal to F0 of Z plus sigma F1 of Z. Again, this is what's coming from the first term, where F0, so now F0 of Z is equal to sum M equals 0 to N0. So I'm writing the first thing, AM0 Z to the minus M. But now, this comes with plus sum 1 minus N0 of Z. So remember that the N0 depends on Z. So it's Z to something of Z times S1 divided by 2 pi I, so our Stokes constant, sum, and now I can't, sorry. Okay, sorry, this is going to be in 2 lines here, unfortunately, because it doesn't fit. So, because remember that the N1 is N0 divided by 2. So now I'm taking only half of the terms, minus 1. AM1, so the coefficients of M1, of the phi 1, times what is called a hyperterminant. And what's a hyperterminant? So this is why it becomes a bit more, why I said that this is just to include level 1, right? These are weird formulas, but again, if you analyze properly the remainder, these are the formulas that you obtain. It's not that these come from nowhere. So let me just write what a hyperterminant is. A hyperterminant, F1 hyperterminant, is, sorry, just a second. F1 is given by exponential of A omega plus I pi m, omega to the m minus 1, gamma of m, gamma of 1 minus m. This is the incomplete gamma function, by the way. So, and I wrote here that I have an F0 and F1. F1 is just, in this case, F1 is really just e to the minus az, is the optimal truncation of the first exponential. Z to the beta sum m equals 0 to n0 over 2 minus 1, a m1 z to the minus m. So F1 is the honest optimal truncation of the phi 1, but as you can see, the next level in this optimal truncation way, the next level to do optimal truncation is not just doing optimal truncation of the first and the second. It's more than that. And this actually, if you were to write those plots, what you end up having is something like this, and then the error keeps on decreasing. afterwards. And then, of course, if you added more terms, it would start increasing unless you add the next. So this has double exponential accuracy. It does give you a functional form, so you don't have to do integrations like with the Borel transforms. But there's two things. Adding more exponentials, the formulas start becoming more and more complicated, of course. You have higher hyperdeterminants, it becomes more complicated. And also, it's discontinuous. Why is it discontinuous? We're doing optimal truncation. So you change Z, and at some point, you're changing the numbers of the truncation points. So when you're talking about Z very large, you don't see anything. But if you're starting to take Z smaller and smaller, then, you know, changing N from 3 to 4 makes a huge difference. So it does, you do see it. So now Borel summation. Let me just see, yeah. So perhaps, we've spoken a little bit about all of these, by the way. It's not, I'm reviewing in some way. I will add some extra things at the end, but now I just wanted to mention. So Borel summation, as we wrote, it's the Laplace transform of our series for each sector separately. I'm writing now here in the positive real axis. So what are the caveats? We often don't know phi n in closed form. We have finitely many terms. What do? We need to actually, so we need to approximate this and using, for example, what we wrote, Pade approximants. And what we have, in fact, is a resummation of that order for each one of them. So, and then it's Borel Pade of order n of phi n of t. This is an approximation. One good thing is that it doesn't matter what the optimal truncation is. If you add more terms, it's not going to make it worse. So you can add whatever terms that you have of all the sectors you have. Of course, if you have these many terms, that would be the terms that you would need for optimal truncation of some level, hyperasymptotics of some level. In principle, you should get the exact same result, or approximately the same result. But these are different. One of the things is that I need to do this integration for each z. Here, in principle, I have a functional form. I could calculate that and plug in the z. But in here, I need to do the integration. If I want different z's, I need to do the integration for different z's. So imagine, exactly, so I've mentioned this, that the F Borel basically gives me the approximation at level n, as long as I have enough terms. So if I have n0 terms, like the n0 of this level 1 hyperasymptotics, I'm going to get the same result. But I need to include phi 0 and phi 1, at least, because that will give me double exponential accuracy, as we know. So if we include in the Tran series, so F Borel of Z sigma being approximated by Sn0 of phi 0 plus sigma e to the minus az S, and let me just write Z beta phi 1. So here, I could write here n0 as well, but in fact, I can write here n0 over 2 because I know that that's what I need for exponential accuracy. So if I had written here n0 over 2, this will give me exponential accuracy the same way. And the other big plus, of course, is that the generalization of this method for different sectors is trivial. Meaning you can do the Borel summation for each sector separately in an obvious way, while here it's a lot of work. So this is what I would like to show you is, so this is for that problem that I spoke about yesterday. And these are the different summations. So, for example, hyperasymptotics, you see these jumps here. Why are the jumps? Because for smaller values of Z, of course, you have, meaning the optimal truncation changes, and there it's quite clear that that happens. We haven't spoken about transasymptotics, so wait a little bit, 10 more minutes, and we'll talk a moment about it. So this is just choosing optimal truncation, but optimal truncation also, of course, it's discontinuous, but optimal truncation only includes the first terms, so it will never be as good as the other ones. So that's the numerical solution. So this is just so that you can see the difference, and basically the difference between Borel-Padé and so do I have here? This is the errors. That's more, that's a clearer thing. Again, ignore the transasymptotics for the moment. So this is the Borel-Padé, and actually the hyperasymptotics. And you can see that the only difference will appear. Level 1 hyperasymptotics. The difference will appear, of course, at early points. Both of these only include the first exponential sector. So if you included other exponential sectors, of course, the accuracy would be better always. So this is just perturbative series and first exponential sector. So now with this, I change and I do my last 20 minutes on which is the last page of the notes. So let's take a look. And now I would ask you to, I mentioned the first time I wrote the Tran series for this problem, I said that I was writing in a particular way, maybe not completely clear what I was doing at the time, but I wrote the Tran series as I had written like that, meaning in the sense that I know that it's sigma to the n, it's the nth exponential, and the z to the beta also shows up multiplied by n, to the power n. So I put everything in n. Why do I do that? Because let me call this tau, a new variable. So of course, tau is a function of z. So, and now I changed the two sums. So here, obviously, what are we assuming? We're assuming that z, so that exponential of minus a z is much smaller than z minus 1, which is much smaller than 1. This is what we're assuming. You're assuming our exponentials are suppressed, are very small. Think of positive real axis, and smaller than these asymptotic series. But we could imagine now, I don't want to stay in that regime in the positive real axis where this is true. I want to expand my solution elsewhere in the complex plane. And in particular, I want to go to regions where the exponential might not be suppressed at all. I still want to keep on assuming that z is small, that z is large, because that's the validity of my asymptotic series. Even though you can, as you see, meaning even for these plots, you can see that actually, so there's W, but that W is the same as my Z, by the way, in the plots. Meaning I am seriously taking, so especially for the previous one, meaning I'm not going to say that, W equals 0.4 is very large. So when I'm saying that actually I can take W to be quite small, and when I was mentioning that to actually make the connection with the results at 0, that it was, you didn't need to go that far off 0. So we can use these asymptotic series. They work very well, the same way as we saw with the Airy function, right? They work very well quite close to the origin. So here it's the same idea. But I want to go, so I want to still stay in the regime where I have my asymptotic series, but now I want to not have to assume this relationship. Might not be true anymore. So actually, I don't want modulus of z here. What I meant is z, because it's z. If z is imaginary, that exponential is of order 1, in fact, but z can still be very large. So what I want is now k, 0 to infinity, z to the minus k, and now I'm putting everything else, tau to the n, ak, n. And I'm going to call this my functions fk of tau. What's interesting, especially if you're talking about nonlinear ODEs, is that you actually have differential equations for these fk's, which, in particular, if the equations are integrable, these are rational functions in general. That's a conjecture. Yes, exactly, but it's not proven. So in general, in the sense of everything that has been done so far, they're rational functions. This problem is not integrable. This is not a rational function. But again, there's a differential equation for these fk's. There's not a differential equation. There's differential equations that you can determine for these fk's. They come from the original differential equation. But one of the main things that is a property of these, so if they're rational functions of tau, that means they're convergent functions of tau, right? Meaning that expression as an expansion in tau is convergent. So the f taus are convergent in small tau. No. Again, this is not the asymptotic series. The asymptotic series is in K. The tree level? A0n. I've never seen it. Meaning, if there could be, again, I think if you start having exponentials of exponentials of exponentials, perhaps you could. If the trans series is to the level of a single exponential multiple, meaning e to the minus n az, I don't think you can. Again, I've never seen a theorem proving this at all. But I don't think you can. But again, if you had a problem where you had exponential of minus az, sorry, no, exponential, it couldn't be with the minus, it had to be with the, in any case, if you had higher levels of exponentials, then I don't know, because then you're talking about, I don't know, a whole, but then you also wouldn't define things in this way. So you'd have to define things in a different way. But as far as I know, these are convergent. So you have these are these functions. Why do I care about calculating these functions? Well, because these actually, like I said, these will allow me to not assume that tau is small. I can take tau to be in different regions, and I can still use my asymptotic series, and I can calculate things like, where are the zeros of these functions? Do these functions have branch cuts? Poles, anything. So in particular, so what I'm saying is that fk's of tau obey ODEs with respect to tau. For example, for this example, and this is a homework to try and find the ODEs, it's not difficult. What you do is you go to the original ODE, you plug in the ansatz, you equate equal powers of z for the fk's, and you obtain the ODEs for these. So f0 of tau is 2/3 of 1 plus w 3/2 of tau. What is w? W is the function such that w of x e to the w of x equals to x. It's the Lambert W function. This is the solution. The higher f's, you can also calculate them. And as it happens, they are polynomials. Should I write, okay, pk. Rational functions of f0. So if f0 was x, these would be polynomial over polynomial of order k. But f0 is not x, it's a Lambert W function, so it becomes more complicated, but these are polynomials, rational functions of f0. And again, you can calculate them. Why is this useful? Again, and I will finish with showing, meaning I still have 10 more minutes, so I will still do the calculation. So so if you analyze the solution of the ODE, the solution of the ODE in the W plane, right, in the Z plane, has branch cuts. Actually, it has an infinity of branch cuts. It has, so the red circles are numerical calculations of the branch cuts. So you basically do you do a Pade approximant, you check the poles where they are of the solution, numerical solution of the ODE, and you find these branch cuts. The blue are the actual, where they start, are the numerical prediction of the branch points. And in green, they're the analytical prediction of the branch points. What I mean by analytical prediction, I'm predicting where the branch points are based on these resummations. Where are the branch points? They're in positions where the exponentials kind of balance each other such that to create those branch points. To create, the solution is actually 0 at those points. I'm not looking at numerical anything. This is analytical. But it's valid for large Z still. That's why, this is why, because I'm still assuming Z large. This is why the first branch point here is not really accurate. But as soon as you start going a bit further, the prediction. But it's analytic. I'll write to you the actual. I'm looking at the zeros of the FKs. I'm actually looking at the zero of the trans series, not the zeros of the FKs. Because each order in the FKs is going to correct for you the zeros. Let me just write it a moment. So what do I want? Meaning there's reasons why you can state that the zeros that you find for this function are all branch points. Because in fact, all of these, because the way these behave, the zeros of these functions are only at the branch points. Meaning of this function, sorry, of the whole thing here, in fact. Because the branch point of W actually starts, I guess the way I've defined it, it starts at -1. Meaning the value of at the branch point is not 0. So what I want is fz, I want to find the values of z where fz tau, and now remember tau includes sigma. So fz tau equals to 0. So these are all square root branch points. And they're related to the square root branch points of the Lambert-Doubly function that happen at tau equals to e to the -1. So W of tau has a single branch point at tau equals to e to the -1. So how do I do this? I assume tau and z at the moment independent. I will introduce the fact that they are dependent and solve for z afterwards. Assume these are independent and solve for now. I say tau of z is going to have some tau 0 plus tau 1 z minus 1 plus tau 2 z minus 2, etc. So what I want is to find an asymptotic expression for tau such that it solves my fz tau equals to 0. Remember that these fk's are higher in z. So if I assume that, I can expand these fk's in z. Like I'm ignoring that tau is, I know what tau is. At the moment, I'm just looking at this expression. I know what the fk's are, and I try to solve this and find tau 0, tau 1, tau 2, etc. So once I have tau 0 and tau 1, then, so whatever, whichever ones you calculate, etc., are determined, then you can, then is when you use the dependence of, so tau is sigma e to the minus az z to the beta is equal to some tau 0 plus tau 1 z minus 1 plus etc. So now you use the fact that you know that tau is is defined as a function of z. And you use this again, you expand for large z, and you can solve this. If you notice, so we had a Lambert W function, and now again, we're inverting a Lambert W function. So when we're solving this, we actually have exponential times z here equals to something that is a function of z. So if you do this, you invert the equations, invert to find z. And what you find, sorry, I know that z is large, right? So I am assuming something is large in this inversion in order to solve for z. And what I'm going to use as z large is, so this comes directly from the fact that in order to invert that exponential, you need to take a log. So you have t is log of plus pi I to n plus 1. And of course, n can be anything, but I'm now taking n to be large. So I'm assuming a variable that is large such that I can still assume that I'm taking a large z approach. And z of the branch points of t are going to be given by t over a. So these expressions come directly from inverting that expression there to order by order. So t over a minus beta over a log t plus 1 over at beta squared log t plus beta squared plus 5 beta minus 3 over a when t goes to infinity. So I'm assuming n large. So to do this, I actually calculated, if I'm not mistaken, I calculated T0 and T1. So I have T0 and T1. I didn't write them here, so I don't remember what they are. But calculating T0 and T1, you can actually calculate this expression. And these are what's there in green for the first few n's. Again, I'm assuming everything that I've done here is valid for z large. This is asymptotic. All of these expressions are asymptotic, which means that in order to actually invert that, I'm assuming that this t, this n is large. If I take n to not be large, like n equals 1, that means that my accuracy is going to be worse. That's, again, why the first branch point there is not exactly correct. But you can see the second one is already quite good, and the other ones are really, meaning the error is quite small. And this is only calculating 2 terms of that tau of z. So you don't have to even calculate more. So that, and this is what I mean about it's an asymptotic prediction, an analytic asymptotic prediction, right? It's not a numerical prediction of the branch points. Something to finish just with a comment. There's something else that you can actually do with this. If you analyze the behavior, meaning the behavior of the solutions, just looking at the differential equation, and you analyze the behavior of the solutions at plus and minus infinity, the behavior is absolutely different. It's completely different, meaning the behavior in the negative real axis is given by logs. And the question that you could ask is, can we see that from the Tran series? So again, it's minus infinity, so z is still large. And you can. How? The best way is to actually write this. Why? Because in minus infinity, these exponentials are large. But once I have the functions f, I can take tau to be large and re-expand the Tran series. And doing that, I will get logs, and I will get the exact expressions. There's a tiny detail about comparing the actual sigmas, meaning there's also an unknown constant, the parameters at plus and minus infinity. And the reason for that is because you have, this is a string, an infinite number of branch cuts. And you need to define where you're crossing the branch cut, meaning where at infinity, meaning how many branch cuts are you crossing, how many are you leaving still after you cross. And that changes the parameters, the comparison between the parameters, plus infinity, minus infinity. But again, my point being is that if you do different summations, you can really probe the complex plane, and you don't even need to stay at the infinity because you can still go fairly close to the origin. Again, do realize that when I write there, this is the complex plane of Z, and I'm talking about Z equals 0.1. That's not Z large. Stating, given that I started with things that assume Z large, we're talking about predictions at quite small Z. It's like predicting the zeros of the Airy function. So, and I think with this I finish. Thank you. The lectures of resurgence are over.
Can I ask you, I didn't forget, so you assume that tau and z are independent, you write that answer, and then you fix E0, tau 0, tau 1, tau 2 by imposing the W expanded Gibson 0. This is how you fix them.
So I'm solving the full trans series at 0, right? So then, because I have, if I want tau 0 and tau 1, that means that very likely you need to include F0 and F1. So it's not enough to include just F0.
And then I still don't quite get it. Why are these necessarily branch points? Why couldn't it just be A0?
So because in fact, because of the behavior of, so large, meaning I'm still assuming large Z, but there's no zeros, there's no more zeros in the W, and these don't introduce more zeros because for each order. So this is higher orders, they're multiplied by Z. So the zeros come from the zeros of of this. And they don't introduce extra zeros. The only zeros of the Lambert W are the branch point of the trans series, but the higher Zs correct the position of that zero, but don't introduce new ones. So some situations, for example, in the, no, actually no, not even in the meaning I was thinking about the poles of the Pauli-Vee, but the poles of the Pauli-Vee you introduce new, but the zeros of the tau function you don't introduce new. They're all there already. The Z just, meaning you can, to be honest, I can't remember the argument, but I remember that we were quite convinced that there was no possibility of any other zeros, in fact. But I can't remember why it was. So poles, like I said, poles, this is not, often this is not quite the case because when you include an extra Z, you need to put everything in the same denominator, and you find that there's poles that start at 1 over Z, for example, instead of starting at constant term. So tau 0 equals 0 is an option, and it starts at 1 over Z, and that introduces a whole level of new poles. But that's not the case here. No one is convinced that these things work.
Can you do this processing topics? You were saying for ODEs, it's one of the cases for which we know.
So I haven't said anything, but even if you, because this is a finite radius of convergence, this is why I wanted to put the finite radius of convergence. You can do you can approximate Padé approximants of these FKs. They're very accurate. And you can find meaning you can use that as your solution. So your analytic continuation given by Pade approximants. You have a finite number of terms in tau, the exponentials, and you approximate it. And you can do a fair amount because in one of the problems that I did, which was with the logistic equation, first time I did it, I hadn't calculated the FKs. I had just approximated them, and I could still analyze the behavior. And the analytic, and more than that, the analytic continuation, because the interesting thing of this is taking the analytic continuation from tau small to tau large, for example. And that's what happened in the logistic equation. So, and you could do that with just a Pade approximant and a few terms. But of course, it's much nicer when you have the ODE and you can actually calculate the functions. I would say yes. But again, you'd have to include high, because each exponential that you introduce will decrease the error to the order of the next exponential, right? So you need to keep on adding, and you are decreasing the error, and you are calculating the real value of your function or your observable. Meaning, what do you mean, of this type of thing, or of just of the regular? But it depends. If you have a nonlinear ODE, you have recursion relations. You can calculate the coefficients of the different sectors. It depends on the ODE, how easy it is to calculate the coefficients. So if you have a trans series that have log sectors, you need to take those into account. But you can still calculate lots. I would say that more than it becomes harder and harder, it's more of that there's a finite amount of time and there's an infinite number of sectors. How far do you want to go? But I wouldn't say that it becomes harder. It's still many. I guess that, so not true. So when you're solving these recursion relations, typically you have a whole part that doesn't, it's the coefficients that you're calculating is equal to something. That something is a sum, very often a sum, of all the previous sectors. That sum becomes bigger and bigger. So in that sense, yes, it becomes harder. Yes? It comes, meaning it's actually all of it comes at the same time, right? It's not that, so both functions, when I wrote, and of course I've deleted. No, but this is the optimal, this is the value that you truncate the phi 0 at, not the phi 1. The phi 1 you're truncating at half of that, so you're still truncating at the optimal, the original optimal point. But the thing is that this makes no sense without the whole hyperterminant coming together with it. Because if you just added that, you'd get a much bigger error. So this comes from the analysis of the remainder, directly from the analysis of the remainder. So With the hyperasymptotics, yeah, you don't have more than the first level, right? So what you'd have is the first hyperdeterminant at the Stokes line. You need to introduce it, and then you have, well, it's like I said, I deleted it, but you have, that is your solution after the the the, the jump.
It looks like in that case, it's way worse, right? Because I cannot continue improving more and more. Once you fix that, you have n01, n00, that is it.
And that's it.
And then there's no next step.
In fact, how does that work again? Yeah, can't remember. Yeah, so basically that you can't. Um, because you'd have double. Huh? Maybe I should. Exactly.